So, now we're mainly going to talk about applications in physics and in string theory, in principle. And the main topics we are going to cover are the followings. So, how to solve PDE, ODE, using neural network. This is actually a well-defined topic and branch of neural networks. And these are usually called PINs, physics-informed neural network. After that, we're going to give a look at dynamical systems. And in particular, we're going to talk about, I'm going to present them in a few minutes, but Hamiltonian neural networks and Lagrangian neural networks. And after that, we make a huge, super huge jump, and we're going to talk about how to find Calabi-Yau metric using neural network. So this, of course, are three topics related to differential equations. And after that, we're going to see an application on learning, line bundle, cohomology, dimensions, and if we have time, but I hope this is the case, we may also look at ways of finding continuous and discrete symmetries. In sort of physical systems. So this is going to be the main application. So let's start with PINs, so physics-informed neural network. First thing to know is this is an unsupervised, I'm sorry for my handwriting. If it is completely obscure, I can try to write slow. Super. So this is an unsupervised method. And in general, as we will see, the unsupervised method is probably in physics the technique we are going to be more interested in, just because in general, how does it work? If you do supervised learning, this means you have a data set, and you want your network to learn something. So you actually need to train it on your data. But of course, you may have extraordinary performances. But on the other hand, the only way this thing can be useful, actually, is if the network is able to extrapolate. So I give you few data. Now tell me what's the result outside of my training domain. There are actually several kinds of situations where networks can perform quite well, and they may actually have a sort of 1% error. But when they extrapolate, of course, the performances are going to become are going to become worse, and therefore we will always need to deal with 96, 95% of accuracy. And this is fine if you want to think about face recognition, is fine if you want to look at something which you cannot model in any other way. But of course, in physics, 96% of accuracy is not enough. Indeed, for instance, if we want to find models which are not in swampland, for instance, and I cook up some strange machine that may be able to distinguish between good and bad models. If I have 96% of accuracy anyway, I cannot rely on the results. I need to actually compute everything by hand anyway, and I do not know whether I'm missing, so if I'm getting false positive on true or true negative. So in the end, I would need to do all the computations anyway. Anyway, let's start with ODE-PDEs. So this is an unsupervised problem. And so, for instance, what we may have is the following situation. So we have a PDE that I summarize here like this, where X, for instance, can be defined on DE, which is a subset of Rn. And U may be a function, let's say ni, so it's number of input dimension, and use a function which goes from r and I to r and o number of output. Now, since I'm not that good in, where is it? In drawing and in writing, as you just see. Oh God, okay. View, read mode, display size, full screen mode. Okay, fabulous. But this is not what I wanted, it's this thing here. So you can actually draw the pointer, okay, it's here, okay. This is not working, but this is working, okay. So what I can actually get, or construct if you want, is a neural network which takes as input my coordinates. Then this is going to be a feed-forward neural network, which means that, of course, you will have a bunch of neurons which are going to compute linear transformation on linear combinations of the input, and then you may have some sort of activation function. So this thing is going to be a huge machinery that is going to output a function. In this case, we have a single neuron, so this thing is going to be a scalar function in this example. And this is going to be a highly non-linear function. Actually, a super complicated function which depends on many, many, many parameters. But as Riccardo told you before, through backpropagation, we are actually able to compute derivatives of this output, not only with respect to the parameters, which are describing your network, but also with respect to inputs. So in practice, I can also compute derivatives of this u of t, x, and y with respect to t, x, and y. So I can compute these things. It's also extremely easy, so we do not really need to write down an horrible code to do that. It's actually pretty automatic in many of the packages that, as TensorFlow, PyTorch, and so on and so forth. And therefore, you see, it becomes pretty clear that you can compute your derivatives and then write down a loss function that in principle may help you in solving, whose minimum is going to be given by something which solves the differential equation you have in mind. Now, of course, if we want to have a well-defined problem, we do not only want to have a PDE, but we need also, for instance, initial conditions. And these are going to be given by and or boundary conditions. Okay, fine. And let's call this thing f of x. Okay. Now, how does that thing work? So first of all, when we need to train a network model, we need to identify our training sample. And in this case, as the problem is unsupervised, we are actually the one who are going to construct the training set. So in practice, for instance, think about this problem of a string attached with the fixed boundaries. So it's defining from x equals 0 to x equals L, and we are keeping the boundaries fixed. What we need to do, this is going to be the domain over which we want to solve the differential equation. We need to sample points at the initial condition and at the boundaries, and of course in the bulk, so inside the domain. Now, if we are able to do that, a suitable loss function which does the job, which means that allows us to find the solution of our partial differential equation. Did you copy this?
Sorry, I have one question.
Yeah.
Where does the actual differential equation come in at this stage?
Exactly right now. I need to write the differential equation, of course, you choose the differential equation you want to study, right? In principle. So we want to study harmonic oscillator. So you write down the equation of motion of the harmonic oscillator, initial condition, initial condition on the first derivative. So the actual So where does the equation of motion or the differential equation comes in? It comes here in here. So your loss function is going to be given. There are actually several ways of doing this, but this is the most intuitive way. It's going to be given by three pieces. Actually, and in particular, all PDE would be nothing but G of X, U, etc. Yes. For instance, I mean, this is an example, but it pretty works. All LIC is going to be given, I called it U of 0, okay. I mean, the last, I presume that the last is pretty easy to understand, but, so what is it? Oh, that is T0. Okay, forgive me. F of X, where of course this averages. So what so I have a bunch of points. I throw them through the network. I compute the derivatives of that horrible thing, which at the moment, I mean, before I start training, that U of T of X of Y is some horrible thing, okay, some random function. Now, my loss function will be defined like this, where I actually, so this bracket are just, mean just an average over your training sample. So here, I'm averaging over points sampled from D. Here, I'm averaging over points sampled from IC, from T equals 0, if you want, or T equal to 0. And this is going to be average over point belonging to the boundaries. This is a piecewise loss function, but it's piecewise, but it's convex, which means that in case through my training, I'm actually able to get to a zero loss function. This means that I'm satisfying the equation of motion, because this is exactly the equation of motion. So if I set this thing to 0, this means that I'm satisfying the PDE. If I can set this thing to 0, at T, on the points that are defined at T equal T0, I'm actually satisfying the initial condition, and here I'm actually satisfying the boundary condition. Is this more or less clear? Hopefully it is. Very well. Now, if you're asking what are alpha 1 and alpha 2, these are just numbers. And the reason is that, it's pretty much well known that if you try to minimize something which is piecewise, so it's convex, but it is also piecewise, you may incur in local minima. So you just end up with your loss function not being 0, maybe it's small, it's not 0. And therefore, this already tells you that you're probably not satisfying your PDEs. But we know that the solution of this problem is unique if and only if I specify the other things. So my personal suggestion, you can try, if you want to try, you can try with just alpha 1 and alpha 2 equal 1. But in general, my personal opinion, this thing, if you put this thing large may, the actual value depends on the problem you are actually solving, but of course you want to enforce these two conditions before actually satisfying the PDE. Because once you satisfy these two initial conditions, the solution of the PDE is going to be unique. Fine. Very well. Now, Now, in principle, this way, we may actually solve a bunch of problems. In particular, we can solve boundary value problems, we can solve initial value problems, we can also solve delayed problems, which are super fancy now because they also model the pandemic, if you want. So you can solve actually quite a lot of different PDEs. The point is the following. I may understand, so given the previous questions, the question from the previous hours, I understand that you do not like that thing and no one actually likes it because that is actually something I do not understand. But no, that is something I do not understand. I do not understand the parameters. For me, that is something I do not really want to work with. But for instance, you may cook up something. I do not have it in the notes, so I really hope it's going to be fine. But you can think about something like this. So if instead, so we still have t, x, and y, or whatever, right? We can have a single layer neural network, single layer, with sign activation function, for instance, or sign activation function. So we have a bunch of sign. So, okay, if I need to follow Riccardo notation, we are going to have some linear transformation here. Okay, a bunch of linear transformation, and then I use on top of this a sign activation function, and then I compute my output. Okay, I call it U, so let's start with U. This is going to be nothing but a discrete Fourier transform, because I'm anyway going to express my function as a bunch of, if you want, maybe it's better if you put another linear layer in the end, so otherwise it's not really it's not really a Fourier transform, but in principle, you can cook up something like this. And when you train this thing, this is actually called Fourier neural network because it can actually give you a sort of discrete Fourier transformation. So, okay, you can use those kind of things. If you like to understand what the hell is happening, you may also use some lighter architectures that, on the other hand, are easy to interpret. Tell me.
No, my question is, this is a Fourier transform but just because of the choice of the activation function.
Exactly, yes, exactly. But then in principle, if you want, you can also use e to the I, omega x plus b, okay? There are these kind of things. And if you use a single neural network, this is nothing but a Fourier transform. And everyone is happy because everyone can understand the output of this horrible thing. So, the same setup can be used also to solve inverse problems. I'm not going into the details because I do not have time. I'm pretty sure I'm already late, but fine. So the main drawbacks of this method are that, as I said, it's unsupervised. It can deal with arbitrary domains because in principle you can just sample whatever kind of horrible thing you want. Therefore, it's mesh-free. And it improves, I mean, it was shown that it improves performances, also improved, let's say, performance on memory complexity for dimension larger than 3, and in time complexity with dimension larger than 5. Compared to what? Compared to finite differences methods or finite elements method. Yes.
Yeah. Can we go back to the loss function?
Yep.
So, imposing the solution of the differential equation and boundary condition initial condition, this amounts to imposing that this LPDF, LIC, and LBC are equal to 0.
Exactly.
Okay, but since L is a sum of squares, I thought that imposing that all the squares are minimum is the same as imposing that L is minimum. So my question is, what is, can I just choose any alpha I and alpha 1 and alpha 2, as long as they are positive?
Exactly, that is the main, yes, that is the main drawback. The point, yes, indeed. In principle, it could be super democratic. The point is that when you take, making a long story short, when you take derivatives of your network, some powers of weights are going to appear, and so this may have some powers of weight that is higher than this, that is higher than this. So this means that the loss manifold is going to be steeper in this direction. And therefore, making a simple example, if your PDE is homogeneous, so think about the harmonic oscillator, it may happen that you end up in a solution which looks exactly like this. Zero. Exactly zero, because zero is a solution, right, in principle. So that is the reason why, in principle, you may need to have an hierarchy there. And of course, the hierarchy you may need may depend, actually no, it actually depends on the problem you're solving. But again, if you set this thing to, let's say, 10 or 100 and 10 or 100 here, in general, this is going to converge. Because once you solve this, if the loss function converges to zero, you're also sure that you're finding your result. But the result is unique as long, or only when you impose the initial and boundary condition.
So in general, I cannot choose freely alpha 1 and alpha 2. There are some subtleties like this type.
Actually, those are hyperparameters within machine learning language, means you can do whatever you want. But if I need to tell you a criterion, that is what I would expect.
Okay, thank you.
Okay, so we are improving performances, yes, so compared to finite difference and finite elements on dimension larger than 3 or dimension larger than 6. This means that if you want to use these things to perform some sort of space-time dynamics, so relativistic simulation, you are on the edge. You do not really know whether you're going to improve or not. But in Calabi-Yau manifolds are in 6 dimensions, so you're actually, so Calabi-Yau threefolds are in 6 dimensions, 6 real dimensions. So in general, you may actually have good improve on performances. Okay. Now, let me check the time. No, I'm not going to check the time. Fine. So, now we can move very, very quickly to dynamical systems. So, in principle, this is a supervised problem. So let's say that you have a fixed system, and you have few trajectories on this system. So for instance, let's assume we have just, a system which, is described by this thing here. Okay, a fixed system. And you look at different trajectories. You have different trajectories on with different initial conditions. But in principle, you would love to find a way to get solution in a faster way. So you would like to have a neural network which may be able to tell you, just given an initial condition, what is the new trajectory without actually computing it. So systems which actually are able to take into account this kind, or are actually able to give you an answer to these questions, are called Hamiltonian neural network. So here, of course, in this particular method, there is something which is implicit. And what you're actually assuming, so you assume that you know, what do you think that you can assume to know about your system is that your energy is conserved. They do not say it explicitly, but I do not think that you can actually use it in a system where the energy is not conserved. So let's assume that we have a bunch of trajectories and that we are able to access canonical coordinates of our system. So we can actually access Q and P on a bunch of trajectories. Now, if I can actually access canonical coordinates, what I can actually do, and okay, in this case I already know there is an Hamiltonian, but let's say I can assume that there is an Hamiltonian that in principle I may not know, okay? And I also know that my particles, or my system, or my trajectories if you want, are going to satisfy the Hamiltonian equations of motion. So, in principle, what one could do is just to, create a network I want my network to learn my equations of motion, and what I can just ask my network to do is I give you a bunch of Q's and P's as input. This is going to be a black box representing my neural network. And I want my network to give me as outcome Q dot and P dot. This, of course, can be higher dimensional, but I mean, let's stay stuck with one-dimensional stuff. Okay, if you try to solve, so this, okay, and let's call this thing I mean, in the paper they actually called it the baseline model. But since you have some physical intuition about your system, you may actually, I mean, this is super straightforward. You may do it if you do not want to think about what, I mean, you actually do it. But in principle, we can do something better, given our physical knowledge on the system. And therefore, we can actually create a network that instead of giving as output Q dot and P dot, it gives us an approximation, of course. I mean, but I put a theta here in the sense that it gives as output a proxy of our Hamiltonian. So in this case, what I'm going to do, I can just, you see, I predict these two quantities, and maybe I use a mean square error as loss function, because this is supervised, so I know. I mean, on my training set, I know these two quantities and these two quantities. So I can just require, so we put a hat here if you want, just to say that this are the network output. And therefore, in principle, I can just cook up a loss function, which may be given by the real Q hat minus the fake Q hat squared plus the real P dot minus the predicted P dot, of course, averaged on my sample. Okay, so I may ask something like this, or so
this is at fixed time.
This is at fixed times. Yes, I'm throwing a bunch of points sampled from trajectories.
Okay. From different trajectories?
Different trajectories. I mean, I need 30 trajectories, so I train the network over all my 30 trajectories. And I can actually request that my network output is this one, and my loss function is this one. I'm not using any, so at this point, let's say, in principle, I know that these are my canonical coordinates, right? But I'm not using any physics here. I'm just saying, okay, I predict this thing, and I actually minimize this loss function, and in principle, if the loss goes to 0, I'm actually finding the solution to my problem.
And in the Hamiltonian, what role does it play there in the training set?
Okay, so no, this was not clear. So this is the baseline model, which is something, I mean, it's just, you know, the most stupid thing you can do on these systems. The Hamiltonian here is what I'm going to use in this other thing, which is actually the Hamiltonian neural network. So the Hamiltonian neural network is a network that takes as input the canonical coordinates and outputs a scalar function, which should be your Hamiltonian, if the training is effective, right? So what is the loss function of Hamiltonian neural networks? Of course, it's going to be by this. Okay, let's keep on averaging. Yeah, I'm always confused. Of course, squared, for instance. So in this case, I'm not using any physical knowledge. In this case, I'm assuming, so let's say I know that these should be the canonical coordinates of my system. Actually, I mean, if I just want to test it, I create trajectories that are based on canonical coordinates, so I can actually do it, if you want, just to test which of the two models works better. I output a scalar function, and I use the Hamiltonian equations in my loss function. So it turns out that, where are these? Okay, indeed, this is more or less what you want to do. So you have your canonical coordinates, you estimate your Hamiltonian, you compute your derivatives, and then you use, so your supervised quantities Q dot and P dot inside your Hamiltonian loss. Well, what happens here is that, in practice, this is the ground truth. Okay, this is a two-body system, gravitational two-body system, nothing more than that. The ground truth, I mean, that you can also estimate analytically, is given by this thing here, where you see that, in general, the total energy is conserved, right? In the baseline model, which is this one here, the energy is not conserved at all, and indeed the two objects start to start spiraling in the output, while Hamiltonian neural networks are actually able, okay, not to perfectly conserve energy, but of course there is a huge improvement. And the reason is that, I mean, baseline models, so neural network in general, tend to dissipate. And if I tell you that they dissipate, it's not clear what the hell is happening. So what is happening, as far as I know, is that neural networks are not good in switching off weights. So they will have some kinds of noise because they, of course, if you have too many degrees of freedom, maybe you would like to switch off some of your degrees of freedom just to clean the signal, but networks cannot do that. And therefore, that's the reason why they are not able to conserve quantities, unless you force them to do that. And in this case, we force them to do that just by using our physical knowledge of the system, in principle. But there is also another drawback here, which is the following. It turns out that compared to this case here, in this case here, the loss function does not depend on the output of the network, but it depends on the derivatives of the network. And the fact that the loss function depends on the derivative of the network is what actually makes it much more stable. So in general, and this is true because, of course, constraining the derivative of the network makes, it implies that for the network it's easier to switch off degrees of freedom and therefore switch off weights. Fine. I do not think I'm going to talk about Lagrange neural network, just maybe a few words, and the words are the following. Here, of course, we assume that we can actually access the canonical coordinates for several models. You cannot really know whether you're looking at canonical coordinates or not. So there is an analogous relation where but I have the picture. I have the picture, yes. So, okay. If you're not sure that your coordinates are canonical, you do the same thing. You just input Q and Q dot. Instead of H, you output or you assume that your network is actually approximating your Lagrangian, and instead of using Hamiltonian equation, you use Euler-Lagrangian equations. Also in this case, so the Lagrangian neural network would be given by a bunch of second derivatives. So also in this case, you are going to be able to conserve the quantities of the system in case the system has any quantity which is conserved. But in practice, this is, it's more, you can use it on, let's say, general systems, but the point is that it's a little bit, computing two derivatives instead of one, and in particular, inverting a double derivative matrix, takes a little bit of time. So these kinds of networks are usually a little bit slower, but of course, depending on the things you want to do, you may need to use this kind of approach and not the Hamiltonian one. Okay.
So just one question, trying to understand the philosophy. What do I gain by doing things this way? In the previous example that you showed with Hamiltonian, we could solve the problem exactly.
Exactly, okay.
So,
but the point is that
I know I can't always solve it.
No, you solve the problem, yes, but because I was starting by something like this. So in this case, you know the energy, and therefore you say, okay, then I solve the equations of motion. Fine. But let's assume that you have some strange trajectory. So I work better with Lagrangian neural network because, I mean, it doesn't happen that you know that those things are canonical coordinates unless you have some sort of formalism that tells you that those are canonical. So let's say that you are just looking at a trajectory, but you do not know the Lagrangian or the Hamiltonian of the system. You may assume, you may have some intuition about the fact that the energy of the system is conserved, but you do not know the form, so the analytic form of your energy. So in this case, you do not need to know the analytic form of your Lagrangian, because you just want the network to approximate it. And in the previous case, you do not want to know the form of the Hamiltonian, because you're just approximating it by a scalar function. And therefore, in principle, if you have an architecture that allows you to look at what is happening here, so what's the functional form of this thing with respect to your initial input, you may also be able to actually write down the Hamiltonian of a system that for you was more or less unknown at the very beginning. So you can also see it as a way of extracting the energy form, so the Hamiltonian from a system.
Okay, so the principle is I have a system to which I can access, whose variables I can access, but I do not know the underlying dynamics.
Theory, exactly.
So some kind of complicated system, and I find an effective Lagrangian that describes those dynamics.
Exactly. Now, for instance, main drawback. In this case here, if you try to use this architecture, but your system is losing energy, this is going to be an horrible mess, and in particular, you're never going to reach any kind of zero loss function, because this kind of architecture works if and only if you're conserving energy.
Okay.
It's implicit.
In terms of applications, where would I find applications of this sort of...
The molecular dynamics,
okay,
blah,
so
blah, blah.
complicated stuff.
Yes, I mean, in physics, we know everything about our system, so we just write down things. Okay, but this, I mean, the two things I just talked about were a warm-up for the much worse thing.
Sorry, I have a literally $1 million question. Now, in the previous case, not the system here, but when you're looking at PDEs, and I was thinking a bit, is there like literally any kind of possible improvement for physicists and mathematicians towards the Navier-Stokes problem? Because you have a PDE.
Yeah, actually, unfortunately, I worked on it. It's rather painful, but in principle, you can find nice solutions to this kind, also to the Navier. I worked in 3Ds, okay? So 2 plus 1D, okay. But in principle, you can find nice solutions, in particular because this kind of method, that one, is powerful in the sense that also if you have not enough information, for instance, you do not have enough points on your initial condition or on your boundary condition, so you cannot actually find a solution with standard methods, the neural network is going to find a solution that in principle, if you construct the network in a certain way, is going to be a good approximation or a first approximation to the final solution.
You can check smoothness or something like this, at least existence or this kind of thing, you can check it this way, right?
Exactly, because then, then of course you can in principle estimate the error the loss function itself is going to tell you what's the error on your solution.
Great, thank you.
Given the information you have. Okay. Now, let me state that I'm not an expert in string theory. So, yeah.
Can I, sorry. So you have a question, but is there any notion of Legendre transform at the level of neural network for the Lagrangian and Hamiltonian one?
It's not a silly question. The problem is that I do not really know.
Okay.
But, I mean, it's probably they tried it. I'm not aware of. I mean, I didn't. I never studied it.
I see.
Okay. Calabi-Yau matrix. Oh my God. Okay. So. Recently, I skipped all the references till here because I'm ashamed. But let me give you this one.
Still regarding this Hamiltonian and Lagrange dynamics.
Yeah.
And from an effective field theory point of view, can you have a Lagrangian or incorporate in this description something that is a high derivative as an effective description.
Yeah, of course.
Okay.
Of course. I mean, the nice thing about this stuff is that, in principle, you can write the loss function as you want. The main point is that, of course, you need to know the equations of motion, right? Because, okay, so Calabi-Yau matrix can wait. What is it? It's here, right? So, let's open a parenthesis. Okay, so in principle, okay, S is equal to the integral dt of L, okay, the Lagrangian, whatever. If I write down the equations of motion on my system, now, okay, I have it written in, okay, let's hope this is correct because, but fine. So this should be the scalar, wow, formulation. So it's double derivative with respect to q dot of L to the minus 1. This is nothing but the equation of motion, and therefore this is going to be what there is called Lagrangian of the neural network. Therefore, I'm forcing the system to follow the Lagrangian equations of motion. So you can extend it, but with the same philosophy. Otherwise, I mean, it's not clear whether it's going to work or not. Okay, fine. Now nothing is going to save me from the Calabi-Yau matrix. So, in this paper here that came out 1 month ago or something, they actually found a way of continuously approximate Calabi-Yau metrics. And why am I talking about this, since I will not have the chance of going through every single detail of this thing, is that probably not that many people in the audience are familiar with neural networks, so I think that the best thing to do would be just to be able to play with it, and therefore these guys released a package which is called CY metric. That is, I mean, whose Python code is inside the second link, but they actually provided, okay, this I can also say, they provided an integration for Mathematica and Sage. So in principle, it's extremely easy to use them just from a Mathematica notebook. And if you want to know, I mean, how to do that, the link is actually Fabian Rule talk at string data from 1 week ago. Therefore, in principle, you can just choose among the, okay, this code works on CCs and on the Kreuzers-Kalk list. Therefore, in principle, you can just choose your favorite Calabi-Yau and just try to approximate the metric and just see how the network performs and so on and so forth without coding too much. And then, you know, choose whether it's worth working with it or not. Anyway, this package is able to work with H11 larger than 0 in a user specified Cala class. And it works again with CC and Kreuzers-Kalk list. So, why is this result important? Not only because networks are fancy and popular, but also because the method that was previously used, as far as I know, and I do not know that much, but to approximate Calabi-Yau metrics was the so-called Donaldson algorithm, which was a fixed point iterative method with some degree. And what this algorithm was doing was approximating the Calabi-Yau metric in monomials of degrees k. Now, the point is that the performance of this algorithm scale factorially with a degree. So, of course, it's not possible, it's not feasible to go to very high order approximations. And therefore and also because of all the other things I told you before, so we actually expect that in 6-dimension, neural networks should actually provide, let's say, better results than standard algorithms. Several people started to ask themselves whether it was worth try to approximate Calabi-Yau metrics with, or several other kinds of metrics with neural networks. Now, a sketch of the system here is going to be the following. So the input, this is unsupervised, by the way. Completely unsupervised method, which means that in principle you should like it a little bit more. So the input of the system is going to be, uniformly, let's say uniformly sampled points on the Calabi-Yau, and the output of the network should be the Keller metric. Actually, this is not completely true, because they saw that actually if you try to do, I mean, of course, here you also have to work with complex numbers, so everything is a little bit more tricky. And they found out that if they directly try to approximate the Calabi-Yau metric like this, so points, network, and G, 3x3 emission tensor, the thing was not working that well. So what they found out, they found a way of improving performances, and the way they did it is that they defined a reference metric, and then the output of the neural network would be just a correction to a reference metric. And I'm going to talk about this reference metric in a second. Actually, they tried several options. So, okay, actually, maybe I can also be super brief about this, but okay. So they tried to compute additional corrections or point-wise, okay, this is going to take too long just to write down something I can just tell you. So additional corrections or point-wise multiplications correction or matrix multiplication, blah, blah, blah. In the end, the best choice would be given just by looking for a correction of this type to a reference metric, and I'm going to tell you in a while what it is, what this is related to, and so on and so forth. Just in order to, let's say, tell you which kind of improvements they were able to get or to reach, they, on the quintic, they compared the Donaldson algorithm with this neural network method, and they find out that the neural network in 2 hours on a standard laptop trained on 10 to the 6 points was able to find comparable results than the Donaldson algorithm in 35 years of training on 10 to the 8 points. So I'm pretty sure this is just an estimate, but this should be the right estimate. So in principle, this thing can be really, really powerful. And now let's look at what they do. Yep. Yep.
Do they give a result as a function of the complex structure moduli, or it only works for a specific choice of complex structure moduli? For example, the quintic has 200 of them.
I think that you can choose them.
So you can. So this is really, really powerful.
I think that you can choose them.
I see.
Even though I'm not swearing this thing, but as far as I remember, you can actually choose them. Okay,
so I pick Kähler moduli, complex structure moduli, and this machine gives me the metric.
Yeah, in principle, it should be like this, but check it and then tell me if it's true.
Yeah. Another quick question is how it deals with the choice of the patch. Like generically, I will have many patches on my manifold. How this machine No, I'm just...
No, it's true. No, you want me to talk about things I do not know. So, indeed, the point is that now I'm going to talk about the network and how the network works. Actually, compared to what I presented previously, behind this work, there is a huge art coding machinery, because they had to find a way of uniformly sample points on the Calabi-Yau. And I think that this is the main reason, because they are using a theorem, and now I'm just citing, by Schiffman, for instance. Exactly, wait a sec. Schiffman and Zeldich, I do not know, it works for you very well, okay, which in principle allows them to find a nice way of projecting points from the ambient space on the Calabi-Yau in such a way that they can sample them uniformly. Then they need to define the top N form. They need to, okay, the ambient space for CCs is for free, but they have the same thing to do with toric varieties. And then they have to define the reference caliform, because this thing is going to come from a reference caliform, which in case of CC is going to be the Fubini study metric. Then they need to define the patches, how to glue them, and blah, blah, blah. So this is actually a huge problem that I cannot talk about because I do not know how it works. And in particular, in the paper, they are not giving all the details, but you may find some of them. I mean, since you actually work in this field, you can actually find some of them in the talk. So probably you will understand much more than I did if you look at it. But I presume you can actually choose whatever you want.
Just asking because it seems like a truly amazing result for string phenomenology to be able to approximate well
Yeah, no, exactly, yeah. Again, okay, you know there is no analytical form for this thing. And so your main problem is going to be that you are not, no, I do not have any picture here then. But the problem is that, as you know, it's not easy to understand what is coming out of there, right? So the final correction, which is mainly going to be given by that phi there, it's a very large series of series, so it's actually not straightforward. In case of CCs, is the Fubini study metric.
So you are talking about the metric of the ambient space?
Exactly,
okay.
Exactly. So, as far as I have understood, they define the Fubini metric in the ambient space, and then there is a way of pull it back.
Yeah, sure.
And that should define a well-defined Keller metric, which of course is not, will not lead you to a Ricci flat metric in general. And indeed, that's the reason why they're actually computing that correction there, because that correction there is going to...
Otherwise, it would be already clear from a long time. No?
Exactly.
If it was the Ricci. But the other, you mentioned the top form.
Yeah.
But that's known from the Poincaré residue formula, no? Why do you need to compute it with this machinery?
I think that the point... Okay, so as far as I have understood, for CC is trivial anyway. Is known.
Yeah.
For toric varieties, you may have problems in defining the affine patches. So the usual coordinate, the usual toric coordinate that you use, are not going to be the one that you're actually using in order to generate all this thing. You need to do a sort of transformation which involves polytopes and therefore...
Sorry, in which case I don't understand? The complete intersection?
In the toric. In the Kreuzers-Kark list.
But still complete intersection?
Complete intersection.
If it is a complete intersection, the Poincaré residue...
No, I think that this thing applies also to...
if you have a non-complete intersection stuff, then it might be tricky to get the omega...
I do not know whether they extended it, because in the paper they published, they mainly talk about cisses. Now I watched the talk there, and they also talk about toric varieties. And therefore, I think that if they were actually able to extend it, because it seems that they were able to extend it to the full Kreuzers-Kark list, they had to do some sort of machinery. That was not trivial to me, not at all. So I'm not an expert, and...
Okay, I will look at the paper.
Okay, fine. So, okay, let's not talk about what a Calabi-Yau is, but let's say that what we want to find is a caliform, okay, and an omega form, so a top form, top holomorphic top form. And in general, so a Calabi-Yau is specified by these two forms, but the point is that J is not unique as far as I know, right? I always look at you so that you can comfort me a little bit. And in principle, you can redefine J in such a way that it belongs to the same cohomology class. Fine. Now, in particular, the Keller metric is just going to be given by this, where K is the Keller potential. And you can actually write down the Ricci curvature as this. I'm not writing down all the indices, forgive me, but I presume they are quite implicit. Okay, and another thing is that we want to use is the fact that we can write the volume of the Calabi-Yau using either J or omega, and this will lead to the following. Okay, I'm not able to write down two types of K. Fine, it's a small k. Imagine it as a small k. Okay, so you can actually write down the volume of the Calabi-Yau as a function of the holomorphic top form or the Keller form. Now, in general, when other people try to solve, so try to find the Calabi-Yau metric using neural networks, what they actually did is they imposed this condition here. So, no, not this condition here, but they imposed this condition here, which is that the manifold, so, okay, that this thing was 0, so that this manifold was Ricci flat. And the point is that if you try to predict whatever kind of output, so, or of metric, and you start to impose this kind of thing, this thing includes 4 derivatives. And therefore, maybe this reconnects to what you said before. Yes, you can actually, compute several derivatives or system which higher derivative systems if you want, but you lose a little bit of precision. And in this case, of course, this metric was a 3x3 in the simplest case. So you were not actually finding satisfactory result. What they were actually able to do in this kind of setting was to actually redefine so J as J ambient space plus this thing, and then impose the Monge-Ampere equation on this correction. And therefore, this should translate to this thing here. At this point, let me write Fubini study. Let's pretend that we are just looking at theses. Okay, fine. If they are able to solve this difference, so this is an implicit partial differential equation for phi, and if you're actually able to solve it, you automatically find the correction to your Keller form, which gives you a Ricci flat. You seem, okay. I know, because I'm not an expert, so if I say something completely wrong, just tell me. If you are able to solve this differential equation for phi, then in principle you are going to work with a Ricci flat Keller metric. Now, the point is that they were not actually interested in solving the full equation for phi. They could just use this thing as a sort of algebraic equation, just because they actually were just interested in this correction here. But in practice, apparently, this is the only way that you're not changing the Keller class when you're actually applying this correction. So the only way of making everything consistent was to actually compute the value of phi, and therefore And therefore, the final network would be given by nothing but it gets as input Calabi-Yau points, uniformly sampled. Here you have nothing but, okay, you will have several layers if you want, but it's nothing more complicated than a feed-forward neural network, so 2 to 3 to 4 layers of something horrible. which makes this, I mean, then of course, you know that the solution is going to be continuous, but it's not that much easy to read. Maybe you need other kinds of technique to, you know, clean up the form of the final solution. And you output phi. Now the question is, given all the information I have, which kind of loss function should I actually use here in order to actually find this scalar field, the scalar function, real scalar function defined on the manifold, in such a way that I'm actually solving the problem. So I'm finding a metric that is that is Ricci flat and so on and so forth. And this is the magnificent result. So the magnificent result is composed by 5 pieces of the loss function. In practice, I presume that in practice they are only using 3 of them. But anyway, the first one is nothing but the Monge-Ampere equation, which means that if this thing becomes 0, you are satisfying the Monge-Ampere equation. GPR is GRF plus this thing, so it's the actual metric, okay? Okay, this in principle comes from the Ricci flatness. If you want, you can keep it in practice since its computational cost is high, they actually neglect it. You impose that the new J is actually Kähler, which means you impose this thing here. And then you impose that the transition is smooth over different patches. D is the number of patches you need in order to cover the full manifold. And so this is the metric defined on patch T, this is the metric defined on patch S, and this is actually nothing but, what is it? It's this thing here. Where I presume that these are actually some affine coordinates that you need to define to get your patches. And this is a constraint which is actually ensuring that the overall volume of the Calabi-Yau doesn't change with this correction. Because apparently the overall volume doesn't need to change, okay? Fine. In practice, the Ricci flatness is going, they have a function which computes it, but just in order to keep track of it, and what they are actually mainly using is the Monge-Ampere equation, the DJ loss function, so the fact that the Kähler form is actually Kähler, and the transition one. And these two are just going to be checked during training. And in practice, they are, with this machinery, they are able to find those results I was telling you before. So, yep. Okay. I know that this thing look a little bit odd, but that's the thing. These are the results they found. So in practice, here they are comparing different kinds of models. So this is, do not look at all the various entries here. These are just the various pieces of the loss function computed on different models. So the free model is the model where you try to directly predict the full metric of the Calabi-Yau directly. The add model is where you compute addition, so additive corrections, and then multiplicative correction and all the other ones. And the model which performs best is, on average, is actually given by phi. The training, since you're actually only computing a scalar quantity, the training is also much faster. And if you notice, we can also try to, make some connection with what we were talking about before, because here, the loss function is going to depend, so it depends only on derivatives on the output of the network. So we know that the performances are going to be better by definition or by experience. So we are actually preventing the network from diffuse. And in practice, the neural network architecture is actually enabling us to add additional constraints to the standard equations that you can usually impose in standard methods. So I know that they do not look fabulous, but once you know that, so let's say the method is unsupervised, the losses are convex, so it's just a sum of convex functions. So if you get a zero loss function, you know that the problem is solved, is awful. Maybe the solution is awful, but it's solved. Okay.
Can you say again the last condition there?
The last condition is that the overall volume of the Calabi-Yau does not change when I introduce the Monge-Ampere correction. This is the Fubini study metric, and I presume that this is the pullback on the Calabi-Yau, and this is the new metric. So in practice, they claim that the overall volume, so the overall volume should not change.
To comment a second on this, so as far as I understand, they take the numerical value of the Kähler moduli as an input. So the volume is already fixed for the pullback of Fubini study, and then they do the correction, and they don't want to change the Kähler moduli. Yeah, because they want to stay exactly same Kähler class. Because so they are. Yeah.
Okay, it's super late, so maybe what I can do.
Let me slow you down even more with a question. So if we strip away the complex nature of the problem and increase the number of dimensions, can we apply something like this to GR?
Yeah.
For different backgrounds?
I really struggled trying to do that. The main problem is the following. It depends which kind of system you want to model in GR. Because, as I told you, the standard errors, so standard loss functions in their minimum are going to give you a sort of percentage error, okay? And maybe if you find the better representation, so in this kind of cases, you want to have a small error in order to perform GR simulations. It turns out that on average, finding the best representation is better than making the network bigger. So for instance, again, I want to solve the equation of motion of an harmonic oscillator. If I choose a sine activation function, I mean, this is trivial, but okay. If you use a single neuron with a sine activation function, you know you're going to find the solution of your problem. And in that case, the loss function is going to be super small. If I try to solve exactly the same thing with sigmoid activation function, on average, the loss function is going to be higher. So, to answer your question, depends which kind of systems you want to solve. I try to solve the collapse of a dust cloud, the Choptwick or Chotwick, I do not remember, it's too strange, but Choptwick collapse, if you want. And the kind of precisions I needed were too high. And the neural network is not able to do that unless you start, adding other machinery on top of it.
And in that situation, what's the input?
In that situation, the input is just, in principle, as the PDE solution you wanted. It depends. If you want to solve a dynamical system, you may try to use sort of Hamiltonian approach or whatever. For instance, by experience, if you want to solve something which has high Lyapunov coefficients, so it's sort of chaotic. Okay, let's say if the system is chaotic and you try to solve it with pins, it's not going to work that well. If you use an Hamiltonian network, it may perform better.
Okay, but there you're in this case you're mentioning, you're exploring spherical symmetry, and you have already an ansatz for the metric.
Okay, yes.
Okay, but well, here
no,
you don't.
Okay,
so that's what I was asking. If you have some kind of general weird distribution of matter that has no symmetries and where we have very little hope of finding solutions to GR.
No, exactly.
That was my question. So is there progress in that direction, or?
Yes, there are people who are actually doing it. They are, for instance, I mean, about cosmological simulation, the best at the moment are, maybe, God, I'm being recorded, but are Miles Kramer and Shirley Hu. They are at the Flatiron building in New York, institute actually, not the Flatiron building. So they do it, but the point is that they need a super huge supercomputer. So yes, you can do something, but not with our laptops. Okay. Okay. Tell me, what do you want me to do?
We started a bit late, so you have 15 minutes tops.
Oh, so I can finally talk about line bundles. Okay, very well. Finally. Anyway.
So, can I ask?
Yeah.
So I have hard time understanding how do you use this knowledge of the metric for string phenomenology, for string compactifications.
In this, so
the knowledge that you get through this method.
Yeah.
Then, since Federico pointed out that this is, basically you don't have a function, but you can evaluate this for any choice of compensation.
Okay.
But what do we need for the compactification is
to
understand. No, well, to understand as much as possible how the metric depends on the moduli fields.
There
right?
are techniques that you can.
There
are techniques. For instance, there is the symbolic regression, if you want, that takes a bunch of input and gives you.
Extrapolates a function.
We are very, very, very far from there.
Okay.
So at the moment, I'm pretty sure that if I try to use symbolic regression to solve whatever comes out of phi, no way that I can do it.
Okay, but that's the goal, basically.
That should be the goal.
Yeah. Okay.
What I had in mind is that stabilize all the moduli, and then so you know what the value, and then you can run this program and get the metric as a function of the coordinates for that specific value of the moduli. Then you can start computing quantities that depend explicitly on the metric, like Yukawa couplings or stuff like that. Yeah.
Okay, I try to be super brief. No way, no way. Okay, so now I'm going to talk about a super specific application. Oh no, I canceled the reference, really. Fabulous. Okay, no, here it is. 1906, 08769. Okay, again, Lucas. So here, what they try to do, and I need my notes because otherwise it's too dangerous. They actually try to compute line bundle cohomology dimensions on complex manifold. If I'm too sloppy, please correct me. In particular, they're going to focus on dimension 2 and 3. And the examples I'm going to show you are coming from CCs and Del Pezzo surfaces. Okay. Then the set of line bundles is given by the Picard group, which you can just imagine as a z to the h. Z here is the integer. Okay, and in the examples we're going to, study, this h is always going to be equal to h11. So, in particular, this is the relation for the Del Pezzo surfaces, and when we're going to look at CC, this means that we are going to look at the most favorable representation. Very well. So, I do not have any time. So, let me just tell you this story. So the story is the following. So we want to predict, okay, let me just write it here, the cohomology dimension, which means that, in principle, I can identify every line bundle with a vector, if you want, we can call it x or whatever, which is just given by an element of z to the h. And we want to predict the cohomology dimensions, which are given by this thing here. Therefore, this is a super specific example, but making a long story short, this paper was born mainly because they did a scan on threefolds, on CCs. And so they actually scanned all, so they had a data set of all this kind of cohomology dimensions. And therefore, the first thing so of course, I mean, they did the scan in for threefolds. In principle, doing the scan for fourfolds was actually, was requiring a huge amount of time and maybe was not feasible at all, apparently. And therefore, they wanted to know whether machine learning could do something about it. So if machine learning was able, or some kind of machine learning technique was able to actually predict this kind of cohomology dimensions. Then, sorry, what is the manifold? See, the manifold, yes, is X. X is a complex. Not necessarily. I mean, it's a del Petzo. The examples I'm going to show are going to be del Petzo surfaces or CCs, threefolds. Okay. Threefolds in this case, and exactly, but then it's going to be clear in a moment. So the training set. This is going to be super short. So the training set was actually given by all the line bundles they had and the, oh God, okay, and the cohomology dimensions that they already computed. So they had a training set like this. So of course, okay, so of course, what they did, they had this training set, so you can, they defined the training set in such a way, because of course you cannot, they had probably many values, so they restrict the training set on Ks, characterized by whatever, let's say 10 or a number, so they restrict them. Let's say if the thing is two-dimensional, they restrict the training set to a square in the Picard group. They divided training and test set, as usual, 70-30%. And then they tried to see, with using a neural network with, in this case, looks like this, so it's super easy. It's the first one, or also the second one, but who cares? I mean, it's a feed-forward neural network, so a simple linear layer, a sigmoid, and then a linear layer. They try to output, so the f theta of k, in this case, should, become a proxy for h of q. Okay, so they tried to predict h of q given some input, some integer vector x, which represents a specific line bundle. Okay. Of course, they got amazing results within the domain of training. They were actually able to get something like 95% of accuracy and so on and so forth. But then, of course, the main goal here was, okay, we do not have a complete scan of fourfolds. So can I just compute a few points for the fourfolds and then just extend what the machine is going to predict? The answer is no, because the accuracy decreases to 70% or so. So the first thing that you immediately understand that, it's not going to save you. So this thing is not going to save you from doing probably a complete scan, unless you can find another kind of application which is a little bit smarter. Fine.
Sorry, one question. So the problem that you're referring to is when you go from 3 to 4 folds. But if you extrapolate within the 3 folds, but
Within
go
the
without...
I just try to extrapolate here.
Yeah.
70% of accuracy.
So it's not very good
That's
there
the problem. Yes, because of course they had in mind, I do exactly the same thing, but for a small box for 4 folds, and then I extend it. Is it going to work? The answer is, well, better than nothing, but no. Fine.
A notation thing. So what is OXK?
So the actual notation I should use, because here they define the divisor, line bundle.
No, that's okay. But you define first a bundle probably in the. So suppose you are talking about a Calabi-Yau manifold, completely. Then you take the ambient space, you take say, the O of something there, and then you pull it back on the Calabi-Yau. That's what you mean by OXK?
I do not have actually.
Because otherwise, I mean, you need. So I guess you mean by this K you mean the charges, no? The projective weights, no? Sorry. Okay, good.
It's a pullback.
Well, okay. If you're working with Del Pezzo, it's already defined what it is, no? So, but okay, good.
Okay.
Yeah.
Okay, sorry. Fine. So, just extrapolation doesn't work. Fine.
So you have a few minutes.
Yes, but I'm going to take only another minute, and it's going to take only another minute or 2, maybe. And then everyone is going to be free. Okay. Then, here, there was a sort of intuition. They had a sort of intuition because from the scan they did, apparently, they found out that Picard group split into different regions, also called, that usually are cones, where the cohomology dimensions is given actually by a polynomial of degree d, where d is the dimension of the complex manifold. Which means nothing that this. So for instance, let's say that I have K0 and K1. In practice, what I saw, just by looking at concrete examples, was that in some regions, for instance, the cohomology class for all the points inside the sort of well-defined region, which is usually, again, a cone, was just given by a sort of polynomial of degree 2. So some kind of function of in this case would be a polynomial of degree 2, okay? Something like this. And then they actually found a way of making this kind of, of machine learning applied to line bundles actually useful. And so what they did was actually the following, so I think I'm just going to tell you the story. They use another network to do exactly the same thing. So they use this network, and I'm going to tell you in a second what this should represent. And they solve exactly the same problem as before. So they give as input integer vectors, and they try to predict cohomology dimensions as output. Now, in principle, of course, they find more or less the same results. They use exactly the same training set as before. So everything, more or less, that I said before applies also now. The point is that now they found a way to make the results coming out of this network interpretable. And the reason is the following. Here we have 2 branches. This part here that I'm calling G theta is actually only going to identify the cones, so the regions in the Picard lattice, while the lower branch is going to find the coefficients of the polynomial. Is it clear or not? Okay. So the point is the following. They trained the network, and what they found is that they after they train all this architecture on the data set, they could define a vector that was actually given by blah, blah, blah. What is it here? So this vector here, this thing here, this thing here, okay, is going to be nothing but a binary vector, which means a vector mainly fulfilled with numbers between 0 and 1. And we actually hope that at some point during training, it converges to a vector of this form. Why? Because at this point, we train the network in such a way that the dimension of this vector is actually the same as the different kind of regions in the P-card lattice. So for instance, let's say that this may be the region 1, 0, 0, 0, 0. This is going to be the region, let's say that this is the other region, this one. This is the region 0, 1, 0, 0, 0. And okay, and so on and so forth. Okay, so this thing is just going to tell you which kind of region we are looking at. So which kind of region the line bundle, so the K vector, is going to belong to. While this thing is actually computing the coefficient of the polynomial. Why? Because if you look, I mean, I have six regions here. Let's say I have 3 regions here, okay? And here I'm actually feeding all the possible monomials coming from the definition of this K. So here we'll have K1, comma K2, comma K3, comma K1, K2, and so on and so forth. Using, I mean, I know what should be the degree of this polynomial. Then this thing is actually going to compute, it's going to output a vector of dimension Rn, where each entry is actually given by a specific polynomial. Because I'm just multiplying, I mean, I'm just, let's forget about B for a second, I'm just multiplying all the various monomials with random numbers. After training, in principle, the network can converge to values of omega 3, which are actually given by the coefficient of my polynomial, of my 6 polynomials. So in the end, I will have one polynomial which corresponds to the entry 1, 0, 0, 0, another polynomial which corresponds to the entry 0, 1, 0, 0, 0, and so on and so forth. Of course, this A is not going to be the output of that vector, but this A is going to be the output of the first branch compared, so this is the output of the first branch, and this one are, in the end, the coefficients corresponding to the polynomial of a certain region. Are you all super confused? Fine. I cannot do much better than this in the time I have. Believe me, this is true. So the network converges. So this is just going to tell, I do not really know how to say it better. So I take this vector here. Okay, let's try it like this. I have this lattice. I throw a bunch of, I use a bunch of points inside this lattice. After a while, the network will recognize that there is some law. I mean, the network was learning the cohomology dimension, so was learning something. At this point, the network should be able, with this architecture, is able to understand what are these regions. So, in principle, the first branch does all these cuts and tells me, for instance, that this is the first area, this is the second area, and so on and so forth. While the second branch here is actually, so just looking at the coefficient, it's just giving me a bunch of numbers. So omega 1, 1, omega 1, 2, omega, okay, let's stop B. I'm not going farther than that. Omega 2, 1, omega 2, 2, B2, and so on, and B, pardon. B is always the same in this case. No, it actually changes, sorry. And this coefficient here, for instance, this is the first line of the matrix, so the coefficients here are going to be the coefficients of the polynomial that you need to apply here, because if you pick a vector which comes from here, the network should actually classify it from the first branch just by 1, 0, 0, 0. So this is so you may have a full matrix coming from here, but what you're actually looking at once you have a precise input is in which area it comes, which is just
to be non-vanishing for line bundles belonging to the first quadrant in these pictures, because that's a Kähler cone, because they are line bundles that are clearly holomorphic. It's L1 plus M L2 with N and M positive. That's the coordinates in these pictures. Okay. They have two sections. They are in the Kähler cone. The discovery is that also for some line bundles that don't belong in the Kähler cone of the original manifold, you can have sections. You can have H0 non-vanishing. For example, the blue zone in the first picture. And what is the interpretation is that you still can have holomorphic line bundles outside of the original Kähler cone. So that is by definition a different flop phase of the Calabi-Yau that you were considering at the beginning. At least that is my understanding of these papers.
We'll let you think. Are there any more questions?
So you were also saying something on overfitting the training set in this particular case. Can you go back to the slide with the architecture, please? Because one interesting point that it may also be in general. An architecture of this kind is usually referred to as multitask learning. It's a very particular case of multitask learning in which you share the weight of the final layers. Usually multitask learner shares the layers, the first layers. This is basically switched. But it was proven that in this case, when you have multiple tasks to learn at the same time, you basically reduce the risk of overfitting by a factor 1 over the number of tasks that you have. So as a general rule, or let's say a general idea in building models, multiple related tasks at the same time. So this basically we learned when we were trying to predict the Hodge numbers of cooking intersection Calabi-Yau. In fact, it was easier to get the network to learn 4 Hodge numbers from Calabi-Yau's implementations rather than having one network output only one Hodge number at a time, even with the full optimization for 4 different networks. And in general, other industrial applications, it's also the same thing. So we actually, when working, for example, with other types of data, which are it's usually easier to use a network which outputs at the same time multiple information. Even though you basically output n information and you discard n minus 1.
Any more questions? If not, let's thank both speakers.
Thank you.
to be non-vanishing for line bundles belonging to the first quadrant in these pictures, because that's a Kähler cone, because they are line bundles that are clearly holomorphic. It's L1 plus M L2 with N and M positive. That's the coordinates in these pictures. Okay. They have two sections. They are in the Kähler cone. The discovery is that also for some line bundles that don't belong in the Kähler cone of the original manifold, you can have sections. You can have H0 non-vanishing. For example, the blue zone in the first picture. And what is the interpretation is that you still can have holomorphic line bundles outside of the original Kähler cone. So that is by definition a different flop phase of the Calabi-Yau that you were considering at the beginning. At least that is my understanding of these papers.
We'll let you think. Are there any more questions?
So you were also saying something on overfitting the training set in this particular case. Can you go back to the slide with the architecture, please? Because one interesting point that it may also be in general. An architecture of this kind is usually referred to as multitask learning. It's a very particular case of multitask learning in which you share the weight of the final layers. Usually, multitask learner shares the layers, the first layers. This is basically switched. But it was proven that in this case, when you have multiple tasks to learn at the same time, you basically reduce the risk of overfitting by a factor 1 over the number of tasks that you have. So, as a general rule, or let's say a general idea, in building models, multiple related tasks at the same time. So this basically we learned when we were trying to predict the Hodge numbers of cooking intersection algorithms. In fact, it was easier to get the network to learn 4 Hodge numbers from rather than having one network output only one Hodge number at a time, even with the full optimization for 4 different networks. And in general, other industrial applications, it's also the same thing. So we actually, when working, for example, with other types of data, which are it's usually easier to use a network which outputs at the same time multiple information. Even though you basically output n information and you discard n minus 1.
Any more questions? If not, let's thank both speakers.
Thank you.